From Kyushu University. I will introduce M2QCode, a model-driven framework for generating multi-platform quantum programs. And here is the outline of this presentation. And first, I will introduce the basic concepts and brief introduction about quantum programming. Current quantum device is still noise intermediate scale quantum device, which means that in the case of hundreds of qubits, noise is very easy to lead to unreliable measurement result, which highlights the need of noise-tolerant method. And nowadays, NTT introduced the concept of invariant programming. This technique involves generating and executing multi-semantically equivalent version of a quantum program across various hardware and quantum programming platforms. By aggregating the resulting probability distribution, it becomes possible to derive high-confidence measurement outcomes. However, generating the invariant quantum programs is challenging, as manual translation between the programming languages is error-prone and time-consuming, while existing tools lack support for multi-language output, making them inadequate for industry deployment. And to solve this problem, we propose M2QCode, a model-driven quantum code generation framework, which can support multi-quantum programming languages and support model for hybrid quantum classical systems. It can model and generate functionally equivalent and executable quantum systems. And here we show a workflow. It uses the UML to model a hybrid quantum classical system and also pass the UML. The classical code generator generates classical part quantum, and quantum code generator generates a quantum program across various programming languages, includes Q#, Qiskit, Barkit, and Circuit. And the first step is to manually model the quantum system through the QuantUML. It includes the system level and the quantum circuit level. And the left shows an example of the shard algorithm system model, and the right shows the bare circuit model. And the code generation part of the classical system is similar to traditional UML code generation. And here we propose the quantum code generation from quantum UML specifications and can generate various quantum programming languages such as Qiskit, Q#, and Circuit. And next is the experimental evaluation. To evaluate the semantic and structural information equality with UML model, we propose research question 1. How effective is the generation of the quantum system? And we use the precision and recall as the evaluation matrix to evaluate M2QCode's capability to extract elements and generate correct elements. And from this table, it shows the precision result and the recall result. The precision recall result indicates the M2QCode can generate more elements than the elements in the UML model. And the recall shows that it generates the element without missing any element in the UML model. So to answer the research question 1, M2QCode demonstrates that generated classical and quantum components preserve the structural and semantic information encoded in the original UML model. And to evaluate the functional correctness of the generated quantum code, we propose research question 2. Can M2QCode generate functionally equivalent quantum code? Here we use KL divergency to compute the difference between generated program output with the standard program output. And a lower KL divergency indicates a higher functionally equivalence. And this table shows a very low KL divergency result of our generated programs. And there are also some missing parts in the table, which due to some gates are not being supported by Q#. But we can replace this gate, use gate decomposition. After report this unsupported gate, it can execute correctly. And the answer to this question 2 is M2QCode can generate functionally equivalent quantum code across multi-quantum programming languages. The KL divergency result confirms that the generated program closely matches the expected output behavior with low divergence value in all supported cases. And last is the conclusion and future work. And we propose the model-driven development framework for automatically generating multi-platform quantum programs, and also introduce support for hybrid quantum classical systems, enabling the generation of both classical and quantum components. And we also evaluated M2QCode through case studies involving 7 real-world quantum systems. The future work includes reverse engineering from quantum code to specification and integration with control flow in quantum circuit. Thank you very much for your listening.